Hello everyone, my name is Amir Kapashev, AAT 2509134, and today I will be walking you through the two techniques for finding the volume of solids of revolution and then showing how derivatives play a direct and practical role in my own field, computer science. First, here is the plan. First, we'll talk about the washer method with full example. Second, the cylindrical shell method, also with a full example. And finally, I will provide you two real examples of derivatives in action. One in machine learning and one in computer vision. So let's begin. And before we start, I want to draw you the picture. We already know how we already know a definite integral can measure the area under the curve. Now take that same flat two-dimensional shape and spin it around the line. This line we'll call it as our axis of rotation. So this sweeps out a brand new three-dimensional solid. And we can imagine a potter shaping the vase on a spinning wheel or a piece of wood on latte. And the whole 3D shape comes from spinning a flat outline around the central axis. And the integral helps us to find this volume. And mainly there are two ways to do it. Slicing perpendicular to the axis gives us disks or washer method. And the slicing parallel to the axis gives us cylindrical shell, our second method. So let's start with the washer method. The washer method is just a simpler extension of disk method. With the disk method, the region touches the axis of rotation, so every cross section is a solid circle. But if there is a gap, so what means by the gap? It means that there is a smaller inner radius and there is an outer radius, as you can see on this diagram. And this shape called a ring or a washer, just like the metal washers that we screw. And to find the volume, we just take we take the area of big circle, subtract the area of the small circle inside it, and integrate that along the axis. That gives us the formula. You can see on this slide the formula of washer method is pi integral from a to b outer radius square minus inner radius square dx. So let's set up and solve using washer method. On this diagram, you can see we have two curves. Is y equals square root of x and y equals x squared. The intersection occurs at the point 1, 1, and the axis of rotation is x-axis. And you can see on the diagram that the square root of x is our outer radius and square root of x squared is our inner radius, as its values smaller than the values of square root of x. So we just simply set up our integral by plugging these values into the formula. So we get v equals pi for integral from 0 to 1. The square root of x squared minus x squared dx. And we solve this just simple integral. We integrate and just plug the values and we get our volume. So now for a different approach, the cylindrical shell method, instead of slicing across the axis, we slice parallel to it into thin tubes like the layers of an onion or a rolled up sheet. So each shell has its own radius, a height, and a very thin wall. There is the idea behind the formula. Unroll one shell into a flat rectangle. Its length is the circle's circumference, 2 pi times the radius. Its height is f of x, and its thickness is tiny dx. And this, when we multiply all these three, add them up with an integral, we get our formula. You can see on this slide the formula of shell method. So shell method setup, we have the y equals x squared. This is our curve. So let's try to take the region under this curve from 0 to 1 and spin it, and we'll spin it around the y-axis. So at any point x, the radius, the distance to the y-axis is just the x, and the height of the shell at that point is just is x squared. So this is the height, is x squared. And now we just simply plug everything into our formula. So we get v equals integral from 0 to 1 x multiplied by x squared. X is just our radius, x squared is our height, and dx is the tiny small this tiny sequence thickness. Then we just solve this simple integral and we get 2 pi x to the fourth power divided by 4 from 0 to 1. We just plug 0 to 1 and we get our volume. So on this slide, I want you to sum up and provide the comparison of two methods. So basically, which method should you use? Simple rule. If the axis matches your function's natural variable, say the x-axis when y equals f of x, then we use the washer or disk method. If you are rotating around the other axis, like the y-axis, while your function stays in the term of x, the shell method saves you a lot of algebra, because you don't have to transfer your equation from y to x as you have to do in the shell in the disk and washer method. So now for the last part, I want to talk about two examples that are genuinely mine, because I'm interested in computer science field, and both use the same tool as before. Take something that is changing, look at its derivative. It's the rate of change, and that tells us something the roll number alone don't show. So example one, I want to start with real-time attention tracking system I built for a class project using a webcam and facial landmarks. The system tracks the eye aspect ratio EAR, a number worked out from 6 points around the eye, showing how open it is. And ER stays roughly steady when your eyes are open, around 0.3 in a typical setup. When you blink, it drops for a few frames, then comes back. And one ER value isn't enough to spot a blink, and normal jitter can look similar. And what actually reveals a blink is how fast ER is changing. And to track the change, we should look at its derivative. So on the slide, you can see the numerical example. So this frame-to-frame differences plus, so we get the first value on the first frame is 0.3, on the second is 0.31, and we can track their difference. And when we have a very sharp drop, minus 19, it indicates that the eye is closing, and it stays low for a couple of frames. You can see that starting from frame 4, 5, and 6, we have relative low value when comparing with the mean. So that pattern, a big drop, then a big rise a few frames later, indicates as a blink, and it's nothing like a normal jitter, which stays small both ways, and it's nothing like drowsiness, where ER would stay long for a long stretch with no quick rebound. This is exactly how real attention and drowsiness system, include the one I built, tell a blink apart from the real attention lapse. So my second example comes from something I follow closely outside the class, is the how market works. And if P of T is an asset's price, say for instance we contain the Bitcoin at time T, then its derivatives tells us the momentum, how fast and in which direction the price is moving. So positives means price is rising, negative means the price is falling. And here is the main idea: whenever that derivative crosses zero, flips from positive to negative or back, that indicates a critical point. And the same first derivative test you would use to find the max or a min of any function in the graph, that point often marks a reversal. Uh, so I want to show you the worked example. Let's look at these real numbers. So I took the latest Bitcoin price in thousands of dollars over 7 hours, and the hour-to-hour change +1, +2, +1, minus 0.5, minus 1.5, and minus 0.5. Notice how the pattern changes. The moment is strong and positive for the first 3 hours. Price is climbing. Then between hour 4 and 5, it flips from +1 to minus 0.5. That's our critical point. Price peaked at at hour 64 at fourth hour, and then hour 5 is where the reversal shows up. And the same idea, tracking price derivatives and watching for sign changes, is behind the momentum indicator and moving average crossovers in real systems. So I want to sum up and tell you why this matters in real world. So both examples use the same idea from this course. A derivative shows a rate of change, and the moments where it spikes or crosses zero are the moments that matter. In blink attention, a spike reveals a blink. In the price data, a sign change reveals a reversal. The same first derivative logic you would use to sketch a graph, and in real life, running inside vision systems and many algorithms every day. So to to sum up, the washer method handles solids of revolution when there is a gap between the region and the axis, giving ring-shaped slices. The shell method slices parallel to the axis instead, often simpler for rotation around their perpendicular axis. And derivatives, that same idea. Power real tools in my field, from spotting a blink on a video to spotting a reversal in the market data. Thank you for your attention.